I just had my cup of coffee and I'm ready to go. Together, let's look at the function f of x is equal to ax squared plus bx plus c, where that leading coefficient a is not 0. We have a second-degree polynomial, and if we graph that on the Cartesian coordinate plane, we get a parabola, which is one of the so-called conic sections. When you're taking an introductory algebra course or perhaps an intermediate algebra course, you learn that the vertex is located on the Cartesian coordinate plane at negative b over 2a, comma, f of negative b over 2a. But the question right now is why? Why is that the case? How do we know that that is the case? If we ask our algebra teacher, the teacher might respond that you have to wait until calculus to derive this vertex from scratch. But that's strictly not the case. We can derive it another way without calculus. In the next video, we'll use calculus, but in this video, we're not going to use calculus. How can we do that? Well, it's just by noticing, observing various patterns of the graph of a parabola. So if we have something like f of x is equal to x squared, approximately we'll get something like this. So here's our x-axis, here's our y-axis. We'll notice that the vertex is definitely at the origin 0, 0. So we can graph that with a graphing calculator. Alternatively, we can create a table of values, plot some points, connect the dots on a piece of paper, that sort of thing. But we'll get something approximately looking like that. And we will definitely know that the vertex is at 0, 0. And we're going to use that as a guide to notice certain patterns, because we can shift or transform that parabola. For example, consider the function f of x is equal to x squared plus 1. So once again, we can pull out a graphing calculator or create a table of values, plot some points, connect the dots, and roughly we'll get something that looks like this. The only difference with x squared is that x squared plus 1 has it that the parabola has been shifted up 1 unit from the origin. Or in other words, the vertex is at 0, 1. Or consider f of x equals x squared plus 6. Same idea, so let's say that's 6. So the vertex has to be at 0, 6. The parabola has been shifted 6 units above the origin. Or finally, consider f of x is equal to x squared minus pi. So if we graph that, we'll notice that the parabola has been shifted down from the origin pi units. So the vertex here is located at 0, negative pi. So just by adding or subtracting a constant, we're shifting up or shifting down that parabola. But we can also shift the parabola left or right. Let's consider f of x is equal to the quantity x plus 1 quantity squared. Once again, we can pull out our graphing calculator, and roughly we'll get something that looks like this. The parabola has been shifted 1 unit to the left from the origin. So we get the vertex at negative 1, 0. The only difference with the parabola x squared is that this parabola has been shifted 1 unit to the left from that origin, 0, 0. Or consider, for example, the function f of x is equal to x minus 72 quantity squared. Roughly speaking, we'll get something like this. So this is 72. And from there, the parabola opens up. So we get the vertex at 72, 0. Now, in an introductory or intermediate algebra course, we also learned that the vertex form of a quadratic equation is as follows. So we get f of x is equal to a times x minus h quantity squared plus our k, where the vertex is at h comma k. And this perfectly models what our observations have been so far. So that k is just going to shift the parabola up or down. That constant is going to shift it by k units. That deals with the y-coordinate, so that is located there. That h is going to be shifting the parabola left or right, so that deals with the x-coordinate. So these observations help to verify the vertex form of a quadratic equation. That models it perfectly. But we can use that information to derive the fact that if we have a function in the standard form of a quadratic equation, the vertex must be this. It must have it that the x-coordinate is located at negative b over 2a. So what we're going to do is the following. We're going to take that function, f of x is equal to ax squared plus bx plus c, and we're going to algebraically manipulate it such that we get it of this form. F of x is equal to a times the quantity x minus h squared plus k. Because then we can just read off the vertex, and we'll notice that, hey, it is negative b over 2a, comma, f of negative b over 2a. So how can we do that? We're going to have to complete the square, because we're going to have a situation where we have this x minus something or plus something quantity squared. So completing the square is essential to this. So the first thing we're going to do is divide the entire equation by the leading coefficient. So we get f of x over a is equal to x squared plus b over a x plus c over a. And I'm going to take this expression, c over a, and so to speak, have it on the left-hand side of the equation. So we'll subtract c over a from both sides of the equation, so it balances. The equality still holds. And we get f of x over a minus c over a is equal to x squared plus b over a x. How do we complete the square? This is one way I think of it. If we think of a plus b quantity squared, we have a perfect square trinomial. We have a squared plus 2ab plus b squared. We want a situation where we have an x plus or minus some constant squared. So we're going to have a term in there, which I will call d, whatever that is, that completes the square. And that d is in this position of b squared in this expression here. Or in other words, think of this, b over a. So b over a right over here corresponds to this 2ab. So we can say that this equals 2 times a. Well, a, in this case here, the leading coefficient is just 1. And b corresponds with this b squared. That's squared, but this is just a b, so it's the square root of that d here. So the square root of d, if that makes sense. And then we can just derive what d is equal to. So d would be b over 2a quantity squared through basic algebra. So that will complete the square. So we get f of x over a minus c over a plus b over 2a quantity squared is equal to x squared plus b over a x plus b over 2a quantity squared. Now this right-hand side should perfectly correspond to a perfect square trinomial. In other words, this should be x plus b over 2a quantity squared. And we can verify that. So if we just multiply that out, so to speak, we will end up back here at x squared plus b over a x plus b over 2a, that quantity squared. Great. And then we have this left-hand side, f of x over a minus c over a. Let's just square that. So that's plus b squared over 4a squared. Let's just add these. So we have f of x over a. We don't have common denominators, so we have c over a. Well, we can times the numerator and the denominator by 4a. So we have 4ac over 4a squared plus our b squared over 4a squared equals x plus b over 2a quantity squared. So we get f of x over a. I'm going to say plus b squared minus 4ac over 4a squared. And the right-hand side stays the same. Let's subtract that from both sides. So now we have f of x over a is equal to the quantity x plus b over 2a quantity squared minus b squared minus 4ac over 4a squared. We'll multiply both sides of the equation by an a, so that we get f of x is equal to a times the quantity x plus b over 2a quantity squared minus, well, to be careful, I'm just going to write this out here. So a times b squared. Actually, let's rewrite this a little bit. Okay, I'm going to resort to the community rule again. I'm sorry. I'm going to move the 4ac to the front of it, so to speak. So we'll say minus 4ac plus b squared, because I just like how that looks better. Let's continue this. Okay, so a over 1, and then we have this 4a squared, so we just get a minus 4ac plus b squared over 4a. Let's deal with these negatives here, because I don't like that. So f of x is equal to a x plus b over 2a quantity squared. So I want a plus there, so I can do it this way. So that's plus 4ac minus b squared over 4a. Great. So this now is of the form f of x equals a times x minus h quantity squared plus k, where the vertex is located at h comma k. And now we can just read off the answer. So h corresponds to this. But notice here we have a plus, here we have a minus. So the vertex must therefore be at minus b over 2a, comma, what's k? Well, k is this thing here. So that's 4ac minus b squared over 4a. And that right there should be equivalent to f of negative b over 2a. And we can check that, by the way. Let's do that. So let's just test this. So we have f of x is equal to ax squared plus bx plus c. So what's f of negative b over 2a? So we have a times negative b over 2a, that quantity squared, plus b, negative b over 2a, plus our c. So let's just square that. So we get b squared over 4a 4a squared minus, well, b and b, so b squared over 2a plus our c. That a is over 1, so we get b squared over 4a minus b squared over 2a plus c. We don't have common denominators. B squared over 4a. B squared over 2a. Let's just times the numerator and the denominator by 2. So we get 2 b squared over 4a plus our c. So b squared minus 2b squared. So we have negative b squared over 4a. So c is over 1. So let's times the numerator and the denominator by 4a. So we have 4ac over 4a. That's minus b squared plus 4ac over 4a. Or in other words, it's the same thing as 4ac minus b squared over 4a. But that's the same thing as what we got up here. We got our vertex as 4ac minus b squared all over 4a. So that works. And we have derived the vertex. The vertex really is at negative b over 2a comma f of negative b over 2a. We didn't use calculus. We just used some intuition. We know by just observation that this vertex form of a quadratic equation perfectly models what is going on. So we just transformed the standard equation into this equation here and derived our vertex. I don't know about you, but I think that's pretty cool. And I remember when I first was studying this many moons ago, I wanted to know, how the heck do we know that the vertex is at negative b over 2a? How do we know that's the x-coordinate? And this is one way to derive that. And I think this is a really good exercise. I hope this video has been helpful to you. I'm the Amateur Logician from amateurlogician.com.